small o and small omega notation. Small o notation. Okay. Small o notation, just we have seen the big O notation, and in case big O notation, we generally keep bigger circle, and for the case of the small o notation, we just go for the small one. So whenever you are supposed to use the two notation, big O of n plus, say for example, small o of n, this is. So sometimes people may confuse whether this is the small o or this is the big O. So explicitly you can mention that okay, big O of n and this is the small o of n. Whenever you feel that okay, there is a confusion, then you can, because we are using the similar symbol for denoting the big O and small o notation. So small o notation provides asymptotic upper bound that is not tight. So in case of big O notation, we have seen that big O notation may denote the asymptotic tight bond, or it may not be, the bond may not be the tight. So asymptotic notation big O denotes the upper bound of any algorithms. So we are saying the worst case behavior of your algorithm. This is the upper bound of your algorithm. So we are also using the small o notation for denoting the upper bound. But in this case, whenever you are using the asymptotic notation small o for denoting the upper bound, then we are sure that the bound is not tight. The bound is not tight means the you have specified the weak upper bound of your algorithm. Although someone may go for the analysis and he or she may find that okay, the uppercase of your algorithm is less than the specified one. So whenever you have seen that okay, roughly you have estimated you have come to know that okay, the bound of the your algorithm, and you have not done the accurate analysis, accurate computation of the determination of the number of operations, but you feel that okay, this may be the maximum upper bound, your algorithm will not take more than this operation, so you are going to provide the loose upper bound. And once you are going to provide the loose upper bound, then you are saying that okay, this is the upper bound of your algorithm, which is not tight, means the uppercase of your algorithm may be less, but your claim is that it will not be more than this. So for safe side, actually you have specified the weak upper bound. Although someone may determine the exact number of operations, then the number of operations may be less than this. So somebody has specified the analysis with the help of the small o notation, then you have the further room to go for the computation of the analysis, as the intuition of this notation is to not denote the tight bound. So you come to know that this is not tight, means that if you go for the algorithm carefully, then you may find that okay, you may be able to obtain the tight bound, and that tight bound will be less than this weak upper bound. We have the notion of this, and once you see this carefully, then you will come to know that f of n is less than c into g of n. In case of the big O notation, we have mentioned here that less than or equal to, but in case of small o notation, all f of n will be here when this condition satisfied. This means the f of n, rate of growth of f of n is less as compared with the rate of growth of c into g of n. So f of n should be less, not equal to, f of n should be less than c into g of n. So you can say that when n tends to infinite, then f of n becomes insignificant related to g of n. So this is one difference. You notice that instead of less than or equal to, we have just used the less than sign, and other one is here for any positive constant. In case of the small big O notation, we have mentioned that there exist positive constants cn and 0. It means if you can determine some positive constant c and n0 for which your relationship holds true, which is the f of n is less than or equal to c into g of n. This was in the case of the big O notation. Okay? So in case of big O notation, we have less than or equal to sign. And we have mentioned that for there exists some positive constant. Means you need to determine just one positive constant c for which you have the value of n0, such that you have the condition like this. But here you can notice the difference that in case of the small o notation, what we mean that for any positive constant c greater than 0, there exists a positive constant. So for every positive constant c, we should have this kind of relationship. And here the rate of growth of function f of n is less than c into g of n. So we have also the small omega notation, and we denote this notation by writing the sign this w. So this is the small omega notation. And here we have the big omega notation. We have seen the big omega notation, and by intuition, your big omega notation big omega notation denotes the time, minimum time of any algorithm, and you know that minimum time, this may or may not be tight. Okay, means someone must, if it is not tight, then someone may show that okay, this is the minimum time. However, the minimum time of the algorithm may be less. So this may not be tight, big omega notation. While if you are sure that the lower case of your algorithm you are going to denote this is not tight, if you are sure that, then instead of using big omega notation, you just go for the small omega notation. So it provides the asymptotic lower bound that is not tight. This is so we are sure now. Whenever you come to know that okay, somebody has given you the analysis and says that okay, this is the small omega of n square, then this small omega denotes the lower bound. Say somewhat it may denote the lower bound here, and this is the weak lower bound, you know that, and you are sure that okay, this is the weak lower bound, but the claim is only that the algorithm will not take time less than, minimum time of algorithm will not be less than this. However, someone may go for the accuracy, and he or she may find that okay, the lower bound may not be this, it is slightly higher. So this is the weak lower. You know that okay, this I'm going to represent the analysis of the minimum time requirement of my algorithm, and this is not tight, and means for the safe side we are going to represent the weak lower bound. So this is the, so whenever you are writing the small o of g of n, so small o of g of n is the set of all f of n, such that if for any positive constant c greater than 0, it is not the case that okay, there exists, again here for any positive constant c greater than 0, there exists a positive constant c n0. So you have n0, there exists n0 for every positive constant c, so that you can say that f of n is greater than c into g of n. So f of n is greater than c into g of n. Okay. And here you can again see that there is no equal to sign, means you are not saying that f of n is greater than or equal to c into g of n. You are saying that f of n is greater than c into g of n, means rate of growth of f of n is very high as compared with g of n. This means once n tends to infinite, then g of n will become insignificant relative to f of n. So here n is 5 n square plus 10. So what you can write with the help of small o notation, small omega notation? So can you say this is small omega of n square? If you want to so write like this, then what you need to do? you need to determine every positive constant C, for which you have the condition f of n means 5n square plus 10, and this is f of n, this should be greater than some C into g of n means n square. Now you you have some, you must have some n0 for all n greater than or equal to n0 for every C, for every positive C. And see that if you can take C is equal to 1, if you can take C is equal to 1, then this condition holds true, for, and you will find n0 as even 1 also. But if you have that C, if C is equal to, say for example 5, or C is equal to, say, if C is equal to 6, if C is equal to 6, then what happen? Here you have the C is equal to 6, and if n is equal to 1, if you have taken C is equal to 6 and n is equal to 1, so what happen here? If you have the 1, here you have taken 6 n square. So here if you have n is equal to 1, then 5 plus 10 15, and here you have the 6. So even if you have taken C is equal to 6, then here you are having the 5n square plus 10 means 5 1, and this is the 10, and here you have the 10, and C is equal to, here we have 6 and n is equal to 1, so here you are having the 6. So 10 in this is true. So for C is equal to 6, this is true. Okay. So for n is equal to, so if you have the n is equal to 10, then if n is equal to 10, n is equal to 10, then also 10 into 10 square means 100 plus 5 510, and here you have the what? Now if n is equal to 10 here, then see the situation here. If n is equal to 10, so for n is equal to 1, it holds okay. N is equal to 1. Now if n is equal to 10, then here what happen? 10 square means 100 plus 5, 500 plus 10, 510, and this should be greater than 6 times n square means 100 means 600, and this condition fails. This is not true. So whenever you have C, then you have, okay, for C is equal to 6, this condition holds true for n is equal to 1 only. But after, if n is sufficient, n tends to infinite, and means n is sufficiently large, then this condition is not going to satisfy. So see that this is not satisfied for C is equal to 6. If you take C is equal to 6, as you have just taken more than 5, but you can take C is equal to 1 or 2 for a small value of C, then okay, this condition holds true. So for some C this satisfies, and for some C it is not going to satisfy. So once you have C more than 5, once C is more than 5, then you will not find n0 for which you can say that after this value of n0 the condition holds true. So once the constant C is sufficiently large, for the large value of this C, this relationship is not going to satisfy, and hence this relationship holds true if and only if C is small 1, means C should be less than 5. When C is less than 5, then only this condition holds true. So but our definition says that for any positive constant we should have the n0. For every C we should have the n0, and you come to know that for every C we are not having the n0, and hence you are not able to write this. But you can write, say that 5n square, 5n square plus 10 you can say that this is omega of n. You can write like this. So if you are not able to write this, means f of n is greater than this, becomes fail, then f of n is greater than some c into n, and this will be true. Why it is so? Because you know that you will find every for this case 5n square. If you have the 5 n square plus 10, and then you will have some, this should be, this is f of n, and here, okay, this f of n should be greater than some c into n, and c can, you can take any value of c. Even you can take 100, c sufficiently large value, there is no issue. C can be small enough. Even you can take c is equal to 100, then surely you will find some value of n0, for which you can say that n, for every, this relationship holds true for every value of n greater than or equal to n0. Why it is so? Why it is so? Because you know that here this is the linear function, polynomial of degree 1, and this is the polynomial of degree 2. And once n tends to infinite, maybe for a small value of, okay, so when n tends to infinite, then the rate of growth of n square is very large. Okay, so when n tends to infinite, rate of growth of n square is very large as compared with the polynomial of degree 1. And so c is the constant, and constants are constant. So whatever constant you can take may be sufficiently large, there is no issue. There must be some value of n0 for which you can say that this is higher than this. After that, this will be more than this. Whatever you can take. For a small value of n, this condition may not hold true. But for sufficiently large value of n, you are sure that, okay, rate of growth of this is very high, and these lower order terms will become insignificant relative to n square. And hence, once n tends to infinite, means n is sufficiently large, then the relationship will hold true. So even you can take c is very large in this case, since the rate of growth of the polynomial of degree 2 is higher as compared with the rate of growth of linear, and hence asymptotically when n is sufficiently large, then you will have the value of n0 which is sufficiently large. After that, this, you can say that 5n square plus 10 is greater than some c into n, and hence if this is true, then you can say that 5n square plus 10 is omega of n. Now you see, small omega notation denotes the asymptotic lower bound which is not tight, and it is clear that you are not able to denote the asymptotic bond which is tight with the help of the asymptotic small omega notation. So actually tight bound is what? 2. If you can write 2 here, then it is tight, but you have to write less than 2, and once you write less than 2, then this is not the tight. So asymptotic small omega notation also denotes the lower bound of algorithm, just like big omega notation. But here you are sure that the bound is not tight. So always small omega notation denotes the lower bound which is not tight. Okay. So in this way we have finished all the notations. So we have seen big O notation, big theta notation, big omega notation, small o notation, and a small omega notation. All 5 notations we have seen. And okay, so like if somebody tells you that I is equal to 1 to n, and here you have the I. So see, every time you write the asymptotic notation, actually you are denoting the anonymous function and you know that this is not the particular function. This denotes the group of function that satisfy this condition. Okay, so this is not the individual function. So here, with the help of the asymptotic bond, every time your asymptotic bond appears, it means you are denoting the anonymous function you don't want to name, and the behavior of that anonymous function is, you know that your anonymous function belongs to this particular group. So whenever you have this, you should not mean that this is the big O of 1 plus big O of 2 plus like this big O of big O of n. This is not the case. What you mean by whenever you have written this, whenever you come in the expressions, then every time asymptotic notations is used within the expression, then you should mean some anonymous function. So here actually you need some, here this represents some anonymous function of I, and once you find the exact function of I, then you can substitute the value from 1 to n and you can find the summation. So every time asymptotic notation appears, and you just mean that you are writing the anonymous function. So now we have finished all the notations, and we come to know that intuition of the all notation. Big O notation denotes the asymptotic upper bound, which may or may not be tight. Big omega notation denotes the asymptotic lower bound that may or may not be tight. Big theta notation denotes the tight bound only. Small O notation denotes the upper case of the algorithm which is not tight. Small omega notation denotes the lower case of the algorithm which is not tight. So here we have seen all 5 notations. We have seen the asymptotic notations. Now your asymptotic notation can have the relationship like the transitivity or symmetry or okay transpose symmetry. So how you can compare the function? So can you identify that your asymptotic notations denote the transitivity relationship? Transitivity. So you have seen that we have big theta notation. So we have the f of n, which we say that f of n is big theta of g of n, and we have the g of n is big theta of h of n. Okay. So we have the big theta of, here f of n is big theta of g of n, and g of n is big theta of h of n, like this. So can you say this employ f of n is theta of h of n? See, f of n is theta of g of n. If you confirm that, okay, if somebody says that yes, f of n is theta of g of n, and somebody says that okay, g of n is theta of h of n. So if f of n is theta of g of n and g of n is theta of h of n, is this mean that f of n is theta of h of n? Yes, this is true. Why it is true? Because we know that whenever you write with the help of the theta notation, we are writing the tight bond, and if degree of this polynomial f of n, if degree is of d, f of n is d, then if degree of f of n is d, then degree of g of n must also be d, because they are representing the tight bond. So here degree of g of n is what? D. And you say that g of n is also big theta of h of n. It means degree of h of n must also be d. And degree of h of n is d, degree of f of n is d. Hence you can say that here f of n is d and degree of h of n is d. and you can say that f of n is theta of h of n. So this is the transitivity relation. So see that your asymptotic notation also reflects the transitivity. So your big theta notation reflects the transitivity relationship. Now can you which other notation, you can see the other notation, like we have the big O notation. So we will see that whether they also show the transitivity or not. So f of n, if you are given f of n is big O of g of n, okay, and g of n is big O of h of n, can this imply f of n is big O of h of n? We can verify. If you are claiming that f of n is big O of g of n, this means what? If the degree of this polynomial is d, then the degree of g of n should be greater than or equal to d, because we know that the big O notation may or may not be tied, but the degree must be at least d. So here also, whatever be the degree, say this may be degree of g of n may be equal to d or greater than d. So you can say that degree of f of n is d, and degree of g of n is, say for example, d dash. So what d dash should be there? D dash must be greater than or equal to d. We should know that. So at least d. So here g of n is big O of h of n, and g of n can be degree of g of n is d dash, and hence h of n, degree of h of n may be, say for example, d double dash, and d double dash which is greater than or equal to d dash, and d dash is greater than or equal to d. It means degree of h of n is either same as f of n as or more than f of n, and hence you can say that h of n, degree of h of n, since the degree of h of n may be same as f of n or more than f of n, hence this relationship also holds true. So you can say that your big O notation also provides, also reflects the transitivity relationship. Similarly, if you have f of n is big omega of g of n, and g of n is big omega of h of n, this implies, can you say here f of n is big omega of h of n? Yes, you can say yes. Why it is so? Because whenever you say f of n is big omega of g of n, means degree of f of n may be more than or equal to this. So g of n is big omega of h of n, means degree of g of n may be more than or equal to h of n. So g of n is degree is more than or equal to h of n. So here you can see that f of n degree is more than or equal to, so even f of n has degree more than or equal to g of n, and g of n has degree more than or equal to h of n. It means it is clear that degree of h of n is either same as f of n, or degree of h of n is less than f of n, and hence this relationship also holds true. So your big omega notation also denotes the transitivity relationship. Similarly, if you can have the small o notation, then it is also sure. So in case of the small o notation, if you have the small o notation, then you are sure that degree is greater than d. So degree is greater than d, and here g of n is small o of, if you have like this, f of n is small o of g of n, and g of n is small o of h of n. This imply f of n is small o of h of n. Can you say yes or no? So see, f of n, degree of f of n is d, then degree of g of n is d dash, which is greater than d. And here degree of d, gn is d dash, and h, it is small o of h of n, and then this is maybe degree of h of n is d double dash, and this must be greater than d dash, and hence you know that degree of h of n is greater than d dash, and d dash degree is greater than d. It means degree of h of n is greater than f of n, and hence this is the f of n is small o of h of. This is true. Here you can also say that f of n is small omega of g of n, and g of n is small omega of h of n. This implies f of n is small omega of h of n. Here f of n is d, and it is small omega of g of n. This means f of degree of f of n is more than g of n. So if g of n degree is d dash, so you can say, sorry, here you have the condition reverse. Degree of f of n is more than this. So here if you have d dash, and d dash, and degree of h of n is d double dash, then d dash must be greater than this. So this means degree of h of n is less than d dash, and degree of d dash is less than this. So this means degree of h of n, since h of n, degree of h of n is less than g of n, it means h of n degree is less than f of n, and this is true. So this also satisfies the transitivity. So all 5 asymptotic notations satisfy the transitivity relationship. So can you show that we have some reflexivity relationship also? So see, if you have f of n is theta of, can you say that f of n is theta of g of n? Yes, in this case degree of f of n and g of n is same. So you can say that this is true. So but for the case of the reflexivity, we need same function, okay? So here actually what you need, f of n is big theta of f of n. So just you say that f of n is theta of f of n, means same function. If f of n is 5n square plus, so here we know that this is the tight bond, and hence f of n is theta of f of n. So reflexivity is also holds true. So if you have the f of n is big O of f of n, we can also say yes, because if degree of this is 2, and here is, we know that degree is 2, means degree is d and degree is d. This is okay. You can say f of n is big omega of f of n. This is also okay. Here f of n and f of n degree, if f of n degree is 2, and here we know that f of n is same degree, so g of n instead of g of n is what? F of n itself. So this is also holds true. But in case of the small o and small omega notation, reflexivity condition is not going to hold. And for the case of symmetrivity, only you have the so symmetrivity. So you can say that f of n is theta of g of n if and only if g of n is theta of f of n. So yes, we know that degree of f of n and g of n will be same because this is the theta notation, and hence theta notation, the only theta notation denotes the symmetrivity relationship, and other notations are not going to denote the symmetrivity. So here what we have seen that your asymptotic notations also denote some transitivity relationship and reflexivity relationship and symmetrivity relationship. So this is just the intuition of your asymptotic notations. Okay, so we have covered all the 5 notation, and you just practice and see in the books, and every time you see in the books for different notation, now you have clear about intuition of every notations, and accordingly you can interpret the meaning of the notation whenever you have encounter such kind of notations. So be careful whenever you are using the asymptotic notation for denoting the analysis of your algorithm. So what notation you are going to use, and you should know the intuition of that, and accordingly you you can denote the analysis. So up to here we have seen the intuition of every notation.